Ça marche? Yep, it works. Sorry, it works.
It works. Don't cough, don't sneeze, please.
I'll try.
Okay. Yeah, okay. So we're going to start the second session of this morning. This is about energy materials and applications. And I'm going to present you this, the 4 talks of this morning. And I am Eric Bousquet from the University of Liège in Belgium. And the first talk is going to be given by Brian Dekhill. He's going to talk about toward improved caloric responses using ferroelectrics. Okay, thank you.
Thank you very much, Eric. Good morning, everyone. So it's always a pleasure to attend this conference. And today I would like to show you some recent works we did on calorics using ferroelectrics. This work we started, I guess, 3 years ago. Of course, it involves a lot of people, and especially this guy, Young, a PhD student, but also many other people from different groups. You may see Laurent is here, the group from Agnès Barthélemy. You have seen Vincent just before, and Jim, Scott, Doru Lupashku, as well as colleagues from China like Xiaojie Liu, as well as Xinjiang Meng from Shanghai. So I guess that you have already seen this kind of triangle, and usually why people are using this triangle is to introduce this magnetoelectric coupling between, let's say, ferroelectric part and the magnetic part. Of course, we have seen many talks about piezoelectrics, and we may also imagine to have the same kind of thing with magnetic materials or with magnetization. And here, today, I would like to show you that the caloric part might be also very interesting using ferroelectric systems, ferroelectric materials. And the idea is to couple the electric field, the polarization, with temperature and S here, which is the entropy of the system. Basically, the main idea is to play on the entropy of the system with an external parameter. In that case, is the electric field, but you may have also magnetocaloric coupling if you apply the magnetic field to control the entropy of the system. This trend is a rather hot topic in the sense that more and more people are interested by this field. And this is a slide showing the increase of, let's say, scientific work. This is a report from a review from the group of Neil Mather from Cambridge. And you see that, especially for ferroelectrics, one of the first work was done in the group of Cambridge with Neil and Jim Scott at that time, and where they showed that in case of PZT thin films, you may have rather strong change of adiabatic temperature change using this kind of ferroelectric system just by applying an electric field. This is the green curve here. A lot of work has been done also using magnetocaloric, or you may also apply a mechanical stress, and you have this so-called mechanocalorics, either elastocalorics, if you apply just a uniaxial stress on your system, or barocaloric. In that case, you have to apply an hydrostatic pressure. Yes, I have to change with the other one. Yeah. Actually, ferrocaloric, whatever the ferroic or the parameter is, magnetization, strain, or polarization, might be very interesting for real application, I would say. And especially if you have a look to this coefficient of performance, And you see that in classical, let's say, refrigerators, this coefficient is between, let's say, 1 and 10. For these alternative Peltier coolers, where you are using the thermoelectric properties, this coefficient is rather small, while in case of ferrocaloric system, like electrocalorics, this number can be highest than this one. Of course, I have to tell you that this is a slide just to tell you that it is very interesting to work on ferroelectric for caloric properties, but there are many, many things to do for a better understanding and a real use of this system in real devices. Nevertheless, it is interesting. I hope I will convince you that it might be very interesting for much more people to work on this field. But before, let me just remind you how it works. And this is a slide showing the electrocaloric properties in comparison with, let's say, classical vapor-based refrigeration cycle. Okay, anyway. So let's start. We start with a disordered system where you have dipoles. And then you apply an electric field in the adiabatic conditions. The dipoles then are aligned along the electric field. You have an enhancement of the temperature on your system. You keep the electric field, and then you can remove the heat from the system. This one is still ordered. Then you switch off the electric field, always in the adiabatic process. The disorder of the dipole appears. There is a decrease of the temperature, and then you can cycle your system you can make many, many cycles using this kind of process. So what we wanted to do and what we tried to do is to tackle this electrocaloric effect. And we tried different strategies. The first one is very basic in the sense that we wanted to look for new material which might be interesting for electrocaloric properties. And the idea was easy. We need to have some order-disorder aspect. And maybe one way is to go close to a composition point where you have coexistence or close coexistence of different phases, like in PZT, for instance, exactly here. And then the polarization can easily go from one orientation to another one, and then you can play on the order or disorder of the system. You have a kind of flat landscape of energy, then it's rather easy to go from one place to another one for the dipoles. The other way is to use a multicaloric effect. What I mean by multicaloric, the idea is we have ferroelectrics. Ferroelectrics have the polarization which is sensitive to the electric field. But ferroelectrics are also a ferroelastic system. So if we apply a pressure, a stress on the system, we can also affect the polarization, and then we should be able to modify the entropy of the system. So either we apply the electric field or a strain at the same time, and we may even imagine to apply some magnetic stress on the system, especially in case of multiferroics. So these are my colleagues, electro, magneto, and elasto. And you will see that they are really useful for caloric properties, enhancement of these caloric properties. The third way of doing is to not using ferroelectrics, but antiferroelectrics. And the idea is, antiferroelectrics, we may have this so-called negative electrocaloric effect. Let me just remind how it works. So if you apply a positive electric field, usually in the positive way, the conventional one, you should have delta T increasing, while in the negative case, we have a decrease of the temperature. So depending if you are more coffee or more beer, you have to choose either ferroelectric or antiferroelectric system, or both if you want to combine both effects. both is very good. So let me start with the first strategy that we use. This is just some chemistry at basically. So this is a phase diagram, temperature, composition for this solid solution. And you see that this bond here, this composition, it's close to room temperature. And here you have a kind of competition between the cubic, tetragonal, orthorhombic, and rhomboidal phase, meaning that this composition at room temperature might be very interesting for caloric effect. And this is true because look at this dielectric measurement, and you see that the dielectric constant is highest compared to the left side or the right side composition. This dielectric constant tells you that the dynamic of the dipole is highest than in the blue or black cases. So you have an indication that it might be, this composition might be very interesting for calorics. Then we did it. The measurement, just some details about the measurement. So in most cases, people are measuring this delta T by indirect measurements based on Maxwell equations. And the idea is to measure the polarization as a function of the electric field. We have these nice hysteresis loops at different temperature. Then you extract the polarization, and you plot the polarization as a function of temperature for each electric field that you are applying. We can see that in that case, we have a nice ferroelectric system in the sense that we have the polarization, which is decreasing with temperature and goes to 0 at the critical temperature in the parasitic phase. Already? Sure? Okay. So we can extract this delta T. Then you can see that this delta T is not so huge, but this composition, is highest than the others. So I have to be faster, so let me go faster. There is another way, as I told you, is to use this strategy too through elastocaloric properties. So this is, for instance, polarization as a function of temperature is just a calculation from Landau-Euler approach. We have a BTO single crystal, and then we pull up the system, different pressure. So sigma here positive, different pressure, and you see that we can shift this critical temperature. It means that if I am here in the black curve without any pressure, the polarization is 0, and when I apply this pressure, the polarization from 0 becomes non-zero. So it means that we have a change of the entropy, and then we have associated to this change of the entropy, we have a delta T, which is measured or calculated here. And you see that the values are very close to the one when you apply the electric field. So elastocaloric, in case of ferroelectric, is more or less equivalent, or the amplitude of delta T is more or less equivalent to that of the electrocaloric properties. So it means that if you combine elasto and electro, you may have much highest delta T in your change in your material. I have to skip some I'm already late. Are you sure? Okay. Okay, we are safe. Okay, it doesn't matter. Let's follow with this example. This one is another system that we investigated with a group of Agnès Barthélémy and Manuel Bibes. Is this iron-rhodium system, which is at this temperature a ferromagnetic system. At room temperature is antiferromagnetic. It becomes ferromagnetic at 370 K, if I remember exactly. And this is a classical magnetization as a function of the magnetic field. And you see that we have this hysteresis loop associated to the ferromagnetic property of this system. So it's a nice system in the sense that we have rather good delta T change for this one. But you see, when people started to work on, it was, let's say, 20, 30, 25 years ago. And they forgot it because of this strong hysteresis loop. So the idea here is the problem of the energy that you want to have, if you follow just the black one, the energy that you can store is exactly this one. But you have an hysteresis loop, so it means that all this part is lost. And you see that finally, the energy that you can extract from your system is very small compared to what you may expect at the beginning. So you need to find a solution to suppress, in somehow, this hysteresis loop. So you can look for second-order phase transitions, and then you can avoid it. Or you can use this system, and then do the following thing. Iron rhodium on the top of barium titanate, which is the ferroelectric part. And we showed 2 years ago that there is a very nice magnetoelectric coupling at the interface between this ferroelectric and this ferromagnetic system. And you see that we can control the magnetization as a function of the voltage of the electric field, which is applied directly on BTO ferroelectric. You apply the electric field on BTO, you induce some strain at the interface, and then you modify the magnetic state of iron rhodium that you have. So we have very good or strong magnetoelectric coupling. So the idea is to use exactly this property, and we start at a given temperature, this one, at 0 volt. We don't apply any electric field, and we are in this ferromagnetic state. So these are some XMCD measurement, P measurement. And you see that these, let's say, the colors here are an indication of the ferromagnetic state. And when you apply the voltage, you see that we enter in the antiferromagnetic state. It means that we just modify the critical temperature of the magnetic state by applying the electric field. And then we use exactly this to do that. We start with magneto here, so magnetization as a function of magnetic field, and we have this bad hysteresis loop that we want to avoid. And then what we can do is we call electro, and then we apply electric field. And you see that by applying electric field, we can change. You see, there is a difference here. And if you find the right recipe to suppress completely the hysteresis loop, then everything is done. You have magnetization as a function of magnetic field, on heating without voltage, on cooling with the voltage. So you use the two stimuli to control, or let's say to suppress this hysteresis loop, which is very bad for caloric properties because of losses due to a Joule effect, for instance. But the problem is that we forgot this guy. Remember that. Ferroelectric, magnetic system on the top. You apply the electric field, the magnetic field, in order to completely suppress the hysteresis loop. But what you did exactly, that you use the hysteresis of the magnetic system, and you transfer these losses to the strain which is at the interface of the system. So actually, you didn't suppress all the hysteresis loop, all the loops, all the losses. You just transfer from magnetic losses to elastic losses. So let me just, this one, the last one, antiferroelectric systems. So antiferroelectric are very interesting because you see that because of the shape of the hysteresis loop, you may expect much higher energy, less losses, if you can say in other words. So this is PLZT, exactly the same system used by Mathieu and Scott in 2006. And we see that antiferroelectric, we are heating the system. From antiferroelectric, we go through ferroelectric as a function of temperature. And then we can do exactly what we did before. We extract the polarization as a function of the temperature for different values of the electric field. If we are at high electric field, you can see that we have exactly the expected shape for classical ferroelectric system. The polarization is decreasing with the temperature, meaning that delta T is positive. But in the antiferroelectric part, you see that first the polarization is increasing, and then it decreases. So in this region, the delta T is negative. And this is very interesting because you can combine negative and positive to enhance the global delta T change of your system. So you see that the value that we got here experimentally is close to 5, 6 Kelvin, which minus 5, minus 6 Kelvin, which is a rather strong value of adiabatic thermal change. The explanation was suggested by Jim to try to understand the physics behind this. We have anti-ferroelectric system, but it's not fixed. The dipoles are not fixed like this. There are always some oscillation around this axis. And then when we apply the electric field, this one will follow the electric field, while this one wanted to rotate. And because of the rotation of this dipole, or let's say the amplitude associated, or the movement, or the dynamic, or the disorder associated to this guy, then you may have this enhancement of caloric response here. So let me conclude, because it's time. So I hope that I convinced you that ferroelectric, ferromagnetic, or ferroelastic might be a very interesting system to study for caloric properties. There are many things to do. So you are invited to help in this field. Let me thank my usual suspects and really the people who worked. Thank you for your attention. And just because I saw that some people did this kind of advertisement, there is a very nice poster from Charles. He's sits there. It's an amazing result that he got from photostriction on BFO based on the first principle calculation. And at the same time, 2 days ago, he got a very nice answer from Advanced Material for his review that he did on ferroelectrics. Several years after Vladimir on photoferroelectrics in 1979. And this is another topic for ferroelectric, which is, I guess, very interesting. I spoke about caloric, or let's say thermal change. I think for the photo change, it might be also very interesting. We will have a very good talk. I know Jonathan for a long time. He will give a very nice talk on this topic this afternoon. Thank you very much.
Thank you for this very nice talk. So we have time for 1 or 2 quick questions.
Sorry, I was too long.
Dr. Hill, if I understood right, it's possible to come to conclusion that the more nucleation energy, the better is electrocaloric effect. The more energy.
Energy, yes.
Yes.
Yes, exactly.
So
exactly.
we must look for the first phase transition, the phase transition of first order with big energy of nucleation.
Yes, it's this kind of system. This is what people are looking for, because if you want to have, let's say, giant electrocaloric or magnetocaloric or whatever, you should look for first order phase transition. The only problem with the first order phase transition is the losses. So you have to find a way to avoid these losses. I would say it might be very good to have, let's say, a first order phase transition with a second order phase transition at the same time, somehow. So having the amplitude of the first order, but the softness of the second order. So maybe by going at some critical field might be interesting also.
Thank you.
Thank you.
Okay, thank you. We can move on and go to the next talk. And the next talk is, if the speaker is around, is by Joseph Guzzo from the University of South Florida. And he's going to talk about piezocaloric effect in antiferroelectric PZT, lead zirconate, from atomistic simulations.
Okay. Hello, my name is Joseph Cuso. I'm from the University of South Florida. I'm an undergraduate research assistant in the Computational Condensed Matter Physics and Material Sciences program under the direction of Dr. Ina Ponomareva. And today I'll be discussing the highly tunable piezocaloric effect in antiferroelectric lead zirconate, work sponsored by the National Science Foundation. So the piezocaloric effect is a particular caloric effect. Caloric effects can either be defined as an adiabatic change in temperature and isothermal change in entropy upon the application of external fields, such as a stress field or an electric field. Now, in particular, the piezocaloric effect is associated with the reversible change in temperature upon the adiabatic application of the stress field. Okay. So some questions we had going into this project. Does the piezocaloric effect exist in antiferroelectrics? And if so, what is its sign? Could the sign of the effect be controlled by the applied field? Okay, so can we apply a field and manipulate it in such a way to get the effect that we desire? What's the intrinsic magnitude of the piezocaloric effect in antiferroelectrics? And what's the atomistic mechanism behind the effect? All right. How does the piezocaloric effect compare to the electrocaloric effect or other caloric effects in the same antiferroelectric? And finally, after we make all these predictions and computations, we want to see if we can demonstrate the effect in an experimental setting. So our methodology, it's a computational experiment, so we have to go over the computational details. We simulated bulk lead zirconate by using a 16 by 16 by 16 supercell. The total energy of the supercells given by a first principles-based effective Hamiltonian. All right, so in the total energy, we have antiferroelectric energies, which are associated with the local mode. Antiferrodistortive energies, which are associated with the oxygen-octahedron tilt about the pseudocubic axis. Elastic energies, which are associated with the strain variable tensor. And these coupling energies, okay, which come from the coupling of the degrees of freedom. So for our parameters that we got from lead zirconate, all right, they were computed from first principles. All right, they show the correct behavior that we expect from lead zirconate under pressure, the correct electric hysteresis loops, and the correct phase transitions. Okay, so we're going to start at a paraelectric cubic phase and transition into an antiferroelectric orthorhombic phase. So some of our intrinsic values that we have for this this material in the brackets here are experimental values and ranges that we'd expect. All right, and we see a lot of our values fall within the ranges or near the ranges of experimental values, which is very good. One that may stick out particularly is the Curie point here. We're about 400 Kelvin over, okay. And we're aware of this, and it comes from a lot of estimations used in getting the parameters for lead zirconate and the number of parameters for the antiferroelectric. Okay, so prior to the piezocaloric effect calculations, we needed the sample from 1200 Kelvin to 5 Kelvin in steps of 5 Kelvin. All right, and with equilibrated supercells, all right, we simulated the piezocaloric effect by using the adiabatic Monte Carlo approach that our group proposed years ago. So essentially what the approach allows us to do is to slowly apply a stress field, in this case for the piezocaloric effect, all right, and we include these energy terms called demon energies, which essentially redistribute the energy of our system in such a way to give us an adiabatic process. Okay, and the process is very natural for caloric calculations. It allows us to simulate first order and second order transitions, irreversible and reversible processes, right, and metastable and stable phases. So some details concerning this approach. Our application removal rate of stress is 2 kilopascals per 1 Monte Carlo sweep. And this value is relatively small compared to the maximum value stress field that we applied of 2 gigapascals. Right, and also the temperature and structural properties computed every Monte Carlo sweep and averaged over 10,000 Monte Carlo sweeps. So now to our computational data. So the effects of applied stress on equilibrium phases. All right, so in these three figures here, we have the antiferroelectric, antiferrodistortive, and strain order parameter magnitudes, all right, as a function of temperature for different stress fields. So these red curves are going to give us 0 stress applied, all right. As we tend towards our darker blue color, we're going to have a stronger tensile stress applied. As we tend towards a darker green color, we're going to have a stronger compressive stress applied. All right, and how we computed for the antiferroelectric, antiferrodistortive parameters are given here, just the simple magnitude computation. And the sigma 2 shows that these local modes are associated with the sigma 2 point in the Briel zone. So if we look at these curves here, particularly these first two, keeping in mind our computational Curie point is 400 or 946 Kelvin, we see strong sensitivity, all right, around the Curie point, the transition temperature into the antiferroelectric phase, strong sensitivity on the applied stress that we have, okay? So this strong sensitivity suggests to us that there's a strong piezocaloric effect to be had in this material, right? And the second thing we should note is that as we apply our tensile stress, you see these order parameters are weakened, all right? And as we apply our compressive stress, they're actually enhanced, all right? So this is a good thing to note for our second slide here, or the slide after this one. The Clausius-Clapeyron estimates were also computed for this simulation. All right, from computations, we achieved this value, and estimates give us this value, which are very good. They're on the same order, the same sign, okay, for compressive stress. Now, under tensile stress, there's going to be metastable phases, which are going to irreversibly transition to stable phases, okay? So this irreversibility prohibits us using the Clausius-Clapeyron equation. So now we look at different dependencies on the stress. So here in figure A, we're going to have the piezocaloric change in temperature as a function of stress, the percent change of the lattice parameter, the percent change of the antiferroelectric and antiferrodistortive order parameter magnitudes. Okay. So if we look at figure A here, we see above the Curie point, the computational Curie point, which is given by these green and yellow curves here, we see that we have a positive change in temperature and a rather large change in temperature. Okay, and as we fall into the antiferroelectric phase, which are given here by the blue, red, and black curves, we see that under tensile stress, we have this negative change in temperature, while under compressive stress, we have a positive change in temperature. So we wanted to investigate this. So if we look at the figure C and D here, below the Curie point, which are given by these blue, red, and black curves, we see that, as we saw in the previous two slides, or the two slides back, we saw that the order parameters are actually weakened under tensile stress, right? And we see this here. And we see that they're actually enhanced under compressive stress, all right? So if we look at this in terms of entropy, okay, with these lowering or decreasing of these order parameters, this is going to lead us to an increase in our configurational entropy. So with this increase in configurational entropy, this is going to lead us to a decrease in thermal entropy, which is going to give us exactly what we would expect as a negative change in temperature. And the same argument can be made for these increases to give us this positive change in temperature here. So why this is very important, okay? We see that just strictly under tensile stress, we have this negative change in temperature. So our change in temperature depends on the nature of the stress, okay? So on the inset of figure B here, we have just a basic refrigeration cycle. So if we start from an initial temperature that's in the antiferroelectric phase, we can adiabatically apply this compressive stress, which is going to give us, of course, our positive change in temperature. And we can drain the heat into a heat sink, decrease our temperature, and then adiabatically remove our compressive stress. Now, from here, we're able to utilize that we're going to have a negative change in temperature under tensile stress. So it's going to give us even a larger change in temperature overall for this refrigeration cycle process. So it's very good for applications. Okay. So now we look at the piezocaloric effect in the vicinity of the Curie point. So again, keeping in mind our computational Curie point is at 946 Kelvin. These values are above our Curie point, and here we're in the antiferroelectric phase. Okay. So if we start well above the Curie point, we see that we have a very continuous, the red dots are going to indicate the application of tensile stress. The blue dots are going to indicate the removal of that tensile stress. And the green dots are going to indicate our application of compressive stress, and yellow dots are going to indicate the removal of that compressive stress. Okay, so we see that it's very continuous. Now, as we approach the Curie point, okay, so we're about 4 Kelvin away from the computational Curie point, we see that under tensile stress, we still have continuity, but we have this first order jump about 9 Kelvin here, okay, when we apply our compressive stress. And moreover, it's reversible, right? So it comes back down to our initial temperature here. So why this is important is because we're able to now utilize the piezocaloric effect, or harvest it, okay? Now, if we look in the antiferroelectric phase, and we look here at the tensile stress, when we apply it, it's decreasing as we expect, and we have another jump, raise in temperature here. But what's different from the compressive stress here and the tensile stress is that this is going to be an irreversible process. So we couldn't utilize this for, say, piezocaloric harvesting. Now, next, what we want to do is look at the piezocaloric effect in a wide range of temperatures. So these first two curves up here, tensile stress and compressive stress, all right, these were computed from the adiabatic Monte Carlo approach that I discussed, I think the second slide. Okay. So we see here we have very large changes in temperature, giant changes in temperature, up to 40 Kelvin under 2 gigapascals of compressive stress. And we also see giant negative changes in temperature under tensile stress, again, 2 gigapascals. All right. Now, we wanted to compare this directly to the indirect approach, which was discussed in the last talk. All right, and it's, for our case, the Piezocaloric effect. It's given by this equation here, so we can just numerically integrate it. And so what we see is that the trend generally agrees, but the big difference, all right, would be our magnitudes. All right, so we see that the indirect approach, if we look at the compressive stress here, only gets up to about 20 Kelvin. So this difference in amplitudes, all right, can be accounted for that the indirect approach doesn't count for the first order, the entropy associated with the first order transition that we have in this anti-ferroelectric. Okay. And as I stated before, our direct method will account for that. So we see that for the Piezocaloric effect, really the indirect method is not really applicable to give a appropriate estimate. So now we wanted to compare our results from other experiments. So we can see we have the different effects here and the ratio of the change in temperature to the change in stress field, or just field strength, near room temperature and maximum values. So we see ours here is given in the red rectangle here. And our magnitude compares very well with other Piezocaloric effects that was found experimentally. Okay, but we see our negative sign, which agrees with the electrocaloric effect that was found in the same material. Now, if we look at the maximum value, something very interesting to see is that, especially if you compare it to the electrocaloric effect in the same material, the anti-ferroelectric, we have a very large positive ratio, while in the electrocaloric effect, they have a very large negative value. So this is also very nice for potential applications. So now, the proposed experimental setup to get these strong stress fields that we need to have these large changes in temperature. All right, so here's some of the details of the apparatus. So we're going to want to utilize a beam bending scheme, okay, to give us the tensile or compressive stress that we would want. All right, so we're going to utilize a lead zirconate thin film, about a micron thick, on top of a few micron thick strontium titanate substrate. All right, and a schematic's given here, and we can essentially get the film. Some studies have shown that it can take or withstand up to 2.5 gigapascals of compressive or tensile stress. Okay, so this is definitely feasible in an experimental setting. So now to summarize, all right, we showed that we can have very large changes in temperature, the Piezocaloric effect in the anti-ferroelectric phase, okay, with the stress applied to the orthorhombic c-axis, which is what all this data is from, okay, all those graphs I showed you. Also, we showed that the tensile stress tends to destabilize the anti-ferroelectric phase of lead zirconate, okay, the lowering of those order parameters, while the compressive stress does the exact opposite and actually enhances the stability. Also, a very nice thing for applications is the coexistence of a both positive and negative change in temperature in the same material, okay, starting from the same temperature which you apply that stress. All right, in the light of these recent results, for the electrocaloric effect, giant effects, and lead zirconate, this could open a new direction in the area of functional materials. So I thank you all for your time.
Right, thank you. So we have time for questions. Yeah.
So may you explain why you get this overestimation of a transition temperature? So far I always thought that this effective Hamiltonian is underestimating it, or the transition temperature.
Yeah. Very overestimated. So you're asking how does it affect... Oh, okay, yeah. So if we go back... Let's go right here. Yeah, so we see in the indirect approach we have this initial temperature term here. All right, so you would definitely think that it's going to have a strong effect. So in our calculations using the adiabatic Monte Carlo approach, it won't be, it affects the value, but it's not overly significant. It's not the reason why we're getting these large changes in temperature. The large changes in temperature come from the fact that we're having multiple order parameters being distorted, coming from the mechanical deformation of the system. So this is what we're postulating is given the reason for these large changes in temperature. It's not necessarily directly corresponds to us having a high Curie point. Thanks. Question.
Another question? So I have a question.
Sure.
So in your model, you included just the sigma anti-ferroelectric modes. Is it right?
Yes.
Your effective Hamiltonian, yeah. And then to which extent these results? Because you apply pressure, you have temperature and so on. But we know that with any strain and so on, you can easily shift to, let's say, sigma to S mode or to zone boundary anti-ferroelectric mode or even to the ferroelectric one. And can you improve your model maybe by including the whole branch of dispersion? These ferro, anti-ferro modes? You just include the sigma mode, that can be...
Yeah, I mean, it definitely could. If I understand the question correctly. So, I mean, whenever we applied stress, so these are all from the stress applied to the orthorhombic c-axis, right? And what we noticed along, the other two crystallographic planes is that, in the paraelectric phase, we had the similar results, but in the anti-ferroelectric phase, we had not nearly the magnitudes that we see here. So, I don't know if that answers your question directly or not, but I'm, utilizing other stresses could enhance it, I guess.
Oh, it's more or less that's what I was saying. That's this in your model when you show that you included the sigma mode and the AFD modes.
Yes. Yeah.
But potentially you can have something else than the sigma modes, mostly when you apply the stress and strain. Isn't it?
Like including more modes in the energy term?
Yeah.
Yeah, I would think, because it comes directly. Yeah, we're seeing, it affects all of the degrees of freedom. Yeah, so definitely it'll give us, a larger, configurational change in entropy. Yeah, definitely we can have a stronger effect. Sure.
Okay, thank you. So we can move on and go to the next talk, and we can thank again Joe. Thank you. So the next talk is going to be done by Bin Su from University of Arkansas, and it's going to talk about anti-ferroelectric rare earth substituted bismuth ferrite, a lead-free system for large energy storage density. Right.
Okay. Hello, everyone. Thanks for the introduction, Eric. And first of all, I want to also thank the organizers to give me this opportunity to present my work here. So what I'm going to talk about is using antiferroelectrics for energy storage. So it has been proposed that antiferroelectrics can be used for energy storage as in a capacitor. It can be charged by applying a voltage and discharged by connecting to a load, a resistor. And this is the outline of my talk. First, I'll briefly talk about what kind of energy storage is suitable for antiferroelectrics and what is special about antiferroelectrics. And in the results, we studied this bismuth rare earth ferrite solid solution system. And I'll show you the storage performance. And we also derive a model to interpret the result and provide some insight. So why do we need energy storage? Simply speaking, it's because energy storage can fill the gap between energy generation and energy consumption. Also, we may need more than one type of energy storage to work together. On this plot, many different type of energy storage methods are plotted as functions of capacity and discharge time. Some methods may have a very large capacity but discharge slowly. So it may be good for long-term energy storage, but may not be efficient if the energy generation can have some rapid fluctuations. For instance, nowadays we want to use more energies from renewable resources, such as the wind and the solar power. And these energies may fluctuate when the condition changes, like the wind or sunlight. So in addition to the high capacity storage method, it's better to have high power energy storage that can charge rapid enough to improve the efficiency. Also on the consumption side, for example, this electric car, the acceleration of the vehicle may require a lot of energy from the battery, which is not very efficient. And integrating with high power energy storage that can discharge rapidly can also improve the efficiency. However, the major drawback of the conventional dielectric capacitor is their low energy density. So let's see why antiferroelectrics is promising. As already been mentioned by Brahim in his talk, antiferroelectrics has this special polarization versus electric field double hysteresis loop. At low field, the antiferro phase is stable, and it goes through a first-order transition to the ferro phase at this, we call it E-up field. And if we reduce the field, the ferro phase eventually becomes unstable and goes back to the antiferro phase at this E-down field. And by definition, the energy density is the integrated area with this discharging curve. And it is because of this first-order antiferro to ferro transition that makes antiferroelectrics can have larger energy density than other dielectrics. And the definition of the efficiency is the ratio of the discharging area to the charging area. The difference of these two areas is the loss of the energy density. So to improve the energy density, we want to enlarge the green area. So large polarization of the ferro phase and large E-down field will be good. And to improve the efficiency, we want to reduce the gray area, the loss. And in this case, the smaller difference between the E-down and E-up will be better. Now let's see a specific system that we choose to study, the bismuth rare earth ferrite solid solutions. On the right, we see this experimental phase diagram of BRFO for 4 different types of rare earth elements. And there's a common feature that for low composition and low temperature, the ground state is the rhombohedral R3C phase. If we increase the composition or increase the temperature, the antiferroelectric PMA phase can be stable. And we choose to study this bismuth neodymium ferrite solid solution. And the other BRFO system should be qualitatively similar. And to simulate the PE curves at room temperature, we use Monte Carlo simulation that is based on effective Hamiltonian. And we have used this effective Hamiltonian to reproduce the experimental phase diagram for BNFO, which is in good agreement. And we take a 12 by 12 by 12 supercell, and the rare earth atoms are randomly distributed. Now let's see the results. So we choose the composition of BNFO that the antiferroelectric PMA phase is the ground state. And in this phase, the antipolar vector is along the 110 direction. We studied 4 different orientations of the electric field. First, for field along the 00 direction, there is a first-order transition from the antiferro PMA phase to the tetraclinal P4MM phase. and the polarization is along the 0, 0, 1 direction. For field along 1, 0, 0 direction, the PE curves are very similar to the case of 0, 0, 1 field. The ferro phase is also this tetrahedral P4MM phase, except the polarization is along the 1, 0, 0 direction, the same as the field. And for field that is along the 1, 1, 0 direction, the first appearing ferro phase is a monoclinic CC phase. But if we further increase the electric field, there will be two more consecutive second-order transitions that the polarization changes more or less continuously. And eventually we reach this orthorhombic AMM2 phase with the polarization along 1, 1, 0 direction. And in the fourth case, we apply the field along the 1, 1, 1 direction. And the ferro phase is the R3C phase, polarization along 1, 1, 1 direction. For each E-field orientations, we see that with the increase in composition, the polarization decreases and the critical fields increase. That's a general feature for all the cases. Based on these PE curves, we can calculate the energy density W and the efficiency eta by finding the areas and the ratios. So that's the same figure again. With the same maximum applied electric field, which is 2.6 megavolt per centimeter, let's compare different E-field directions in some more details. For energy density, the 001 field is the best, and also it increases with composition. And the 100 field is basically very similar to the 001 case. And relatively, the lowest energy density is given by the 111 field. For 110 field, it has a comparable energy density as the 001 case when the composition is about 0.4, but it has a weak dependence on composition. For efficiency, the 110 field has the highest efficiency, and it also has a weak dependence on composition. And again, the 111 field has relatively the lowest efficiency. And 001 and the 100 fields are similar, and they increase with composition and eventually becomes comparable to the 110 case at high composition. Based on the behavior of the previous slide, we choose 4 representative cases to further calculate the energy density and eta as a function of Emax, the maximum applied electric field. We choose 3 compositions from the 001 field and 1 composition for the 110 field. As expected, the energy density increases with Emax. The efficiency also increases with Emax, but mostly for Emax that is close to E up, which is this antiferro to ferro transition critical field. If we compare the energy density of BNFO with other same type materials that have found to have good energy densities, we see that BNFO is much better than those light-based antiferroelectrics. It is those dark squares. It is also much better than this polymer dielectric, this so-called PVDF. Only this recently found complex relaxer, BNL-BTZ, has a comparable energy density as we predict for BNFO. And this vertical dashed line is the electric field that has been achieved in pure BNFO thin film. And at this field, the energy density is in the same order as supercapacitors, so it's quite good. Now let's look at the model. So by definition, the energy density is defined as this integrated area with a discharging curve. And to simplify the calculation slightly, we can make 2 approximations. First is we assume the antiferro to ferro and ferro to antiferro transition are abrupt. The second is we assume the dielectric response of the antiferro and ferro phases are the same and as a constant. So by doing so, we can express this integral as a sum of two terms. The first term is the area of this green parallelogram, which is the polarization of the ferro phase extrapolated to zero field times E down. And the second term is the area of this blue triangle. It's 1/2 of the dielectric constant times the E max square. Some of the results can be explained by this expression. Let me go back a few slides here. So for example, the 001 field has a larger energy density than the 111 field because it has a larger polarization, and also the E down is also larger than that. But it's not straightforward to explain the compositional dependence because as we increase the composition, the polarization decreases, but the E down field increases. So they have a opposite trend. To get more insight, we want to expand this first term in terms of some energetic quantities. The idea is that between the antiferro and ferro phases, they are connected by an energetic path. The energy for each point on this path, they change differently under electric field because the polarization are different from zero to the ferro phase. And the antiferro to ferro transition happens when the ferroelectric phase has a lower energy, as well as this kinetic barrier, delta ER prime, can be overcome by the thermal energy. Something similar for the ferro to antiferro transition. Because these two barriers, the delta E down and delta ER prime, are both limited by the same temperature, so we will assume they are the same. Without showing all the details, the final expression is this. And the second term is unchanged. In the first term, we have 4 different parameters. This delta E down is the effective kinetic barrier happens at the transition. And delta 0 is the ferro to antiferro transition barrier at zero field. And this delta EC is the barrier height when the antiferro and ferro phases have the same energy. This energy difference, delta U, the UF E naught minus UAF E naught, is the energy difference between the two phases at the zero field. Now we can use this model to understand the results. For each composition and each E field directions, all the parameters except this delta E down can be obtained by effective Hamiltonian, as shown in these 3 figures. And delta E down can be obtained by B-square fitting to the energy densities and the efficiencies for each E field. We also assume this delta E down change linearly with composition, but it's a weak dependence. That's what we found. The agreement is good, which indicates the model can describe the calculated data rather well. Oh, by the way, so we have 2 parameters to fit each 14 data for W and eta. So then let's see if we can use the model to explain the compositional dependence. For 001 field, we have a increasing W versus composition. This is because this delta U is increasing with composition, and this delta EC is decreasing with composition, and delta EC appear on the denominator. This dielectric susceptibility increases slightly with composition. So all these 3 factors can contribute to the increasing trend. For 110 field, it is has a weak dependence on composition because the delta U slightly increase with the composition and the delta EC slightly decrease, but this dielectric susceptibility decreases, so there's a compensation effect. The other cases can also be explained in a similar way. So in summary, we have predicted the antiferro BFO is very promising for energy storage, and we also expect qualitatively similar results from other BFO systems. With a simple model we have derived, we can understand the results, and it also tells us that to improve energy density, it's better to have large delta U, means more stable antiferro phase or more unstable ferro phase, which can be achieved by manipulating the composition, E-field direction, or epitaxial strain. It's better to have small delta EC, large dielectric constant by using high kappa materials or changing the conditions. And it's also good to have large Emax. Usually thin film can sustain a higher field. And to improve efficiency, it's important to have small delta EC and large Emax. All right, thank you very much.
Thank you, Ben. We have time for one or two questions here.
Very impressive talk. I see that in the abstract, you actually mentioned there's some experimental work achieving about 150 joule per cubic centimeter, and you commented that because of they're using the coexisting phase method, the composition and temperature stability may not be good. And in your model, I see your model, the composition dependence. Some of the orientation can give you stability over different composition. How about temperature stability? Did you do anything about that?
Let me show you some extra slides. Yeah, we actually tried a few temperatures for not all the cases, but a few representative cases, like this 50% 001 field and 110 field for three different temperatures, 200, 300, and 500 Kelvin, and it's pretty stable.
Actually have a quick comment. I'm an experimentalist. I worked with bismuth ferrite for quite a while, 5 to 6 years. I know it's a very tough animal to deal with, especially the leakage current. So such a high electric field, something like 6.5 megavolts per centimeter, I'm not sure if you can achieve. Even though you can achieve in thin films, like really thin films, I'm not sure it will be useful for any real applications because the energy is so low, right? So I think from practical point of view, thick films may be more meaningful. If you have a little bit lower energy, but you have more juices to be able to use, that may be more useful. Just my own comment.
Yeah, I agree. Actually, because we have predicted there's a lot of flexibility in this system. So if in case there might be a large leakage current at high field, so even for those that with a slightly lower energy density or efficiency, those can be achieved with lower critical field. Maybe can still be useful. But thanks for your comments.
My question is whether you need bismuth at all. I'm just looking at these plots on the right. It looks like the 100% neodymium composition is sometimes the best.
Yeah,
is
exactly.
That your view also?
Yeah, that's what we predict. But it's better that it can be verified by experiments. Yeah, we predict this pure NFO has kind of the best result. But it also depends on if they can apply this high enough electric field to the film. That's a problem, maybe.
All right, thank you, Bin. So we can move on and go to the next speaker, the last speaker of the session. What is your first? Okay. next speaker is Maya Kokla from the University of Maryland, and she's going to talk about first principles calculations on structural instability and stability of complex perovskites for solid oxides fuel cells.
Check. Can you hear me?
Yeah.
Okay, so we're switching gears a little bit and we'll be talking about slightly different topic. It's also applications in energy, but we will be talking about materials for fuel cells and permeation membranes. It's a large collaborative project which we were working several latest years. Includes my group at the University of Maryland, Max Planck Institute, University of Latvia, and Ben Gurion University of Beersheba, Israel. So there are a couple of series of materials, perovskites, which we are going to talk about, and mostly my talk will be about BSCF. There are several interesting findings in the community which kind of caused a lot of enthusiasm towards this material. And at some point, people even thought that this is kind of panacea. This is new material which will solve all the problems in energy storage and conversion. It will be great for catalysis, for fuel cells, membranes, batteries, you name it. It will be great. And there was a good reason actually to think this way. For example, this material, the whole series of BSCFs, was considered among the most promising ceramics for cathodes and solid oxide fuel cells and oxygen permeation membranes, because it exhibits mixed ionic and electronic conductivity, which is good for these applications. It shows the best oxygen exchange kinetics known for any solid oxide. It reveals the lowest oxygen vacancy formation energy and low activation diffusion barrier, which kind of leads to very good properties for these applications. All these were good advantages, and that's why people were so enthusiastic about it. However, there were also revealed potential problems with this material, and about 8 years ago, nobody paid too much attention to them, but then researchers got more serious about it. For example, it was known and reported not very consistently in experimental literature that there is considerable scattered with non-stoichiometric parameter delta in these materials, and it was ranging from really low, 0.2 or even lower, to really high, 0.8 or even 1. It also showed slow transformation at intermediate temperatures into a mixture of several phases, including hexagonal phase, which does not have these good properties of regular material. So first it was discovered kind of almost accidentally, as people were making experiments and measured performance of fuel cells with BSCFs. It was great, but then it was difficult to reproduce the results. And in several days, the results were completely lousy. Right? So most of the time, at earliest stages of this research, these kind of results were not reported. But then with first report about hexagonal phase and potential instability of the cubic phase, experimental reports towards this kind of start appearing in the literature. And that motivated us to do our research, which was based on pretty much first principles calculations. So based on these observations and kind of great potential for the material to be used for energy storage and conversion, there are two important questions which raise immediately and which we are trying to address. So one is, can we predict these favorable features and mitigate some problems in this series of materials? And the second one, which is closely related to this, can we design new materials with tailored properties from scratch? Or can we improve existing materials somehow with some manipulations or some treatment of the material, and what can be done? So, which helped us to formulate the whole project goals and objectives. Overall, overarching goal kind of is to understand and significantly improve performance of cathodes for fuel cells and permeation membranes, which means that we need to understand oxygen transport and reduction, material stability and point on end extended defects. The complexity is that all these three issues are interconnected and you cannot understand one without the other one. But all three of them are kind of complex and complicated at the same time. So our specific objectives were to achieve first principle understanding of defect-induced behavior of BSCF material and series of relevant materials, LSCFs, then find correlations between various defects and oxygen reduction mechanisms, and identify trends in structural stability or instability of the material as function of chemical composition, presence of defects, stoichiometry, interactions of these defects, and so forth. And of course, we always want to validate the experiments and build models with predictive power. So all this work is, the results I will be talking about, they are obtained theoretically, but we will work with experimentalists very closely to validate whatever conclusions, smart or stupid, we make. Most of the calculations are performed with VASP, with density functional theory in plane wave basis set. We use large supercells for our calculations. We also used analytical solid state chemistry and some cluster expansion with ab initio thermodynamics in our research. So we started with modeling various disorders with simple kind of defects. BSCF has a cubic structure, and you can see it on the picture. Our model composition for earliest calculations was kind of simplified to start with small supercells. It actually didn't work, and then we enlarged it. Single vacancy was studied for all possible combinations. Then cation sublattice disorder, when you have exchange of atoms within one lattice, another lattice, or between them. Frankel disorder, Schottky, and Schottky-like disorder. We also wrote solid-state decomposition reactions and looked at their energies and enthalpies to make some conclusions about stability of the material. So structure, simple structure, as I said, we started with cubic, and then we populated it with defects. So a simple oxygen vacancy, hollow interstitial defect, split interstitial defect, and cation clustering or cation lattice disorder. So looking at the energy, of course, we looked at different combinations because oxygen vacancy can be situated in different positions between different cations, and energy slightly depends on this. But we looked at all possible vacancies, and among all possible single vacancies in the material, oxygen vacancy, of course, is the most favorable, and its energy is actually very low. It's much lower than for typical perovskites which are used for this kind of applications, including LSM and STO, for example. Among Frankel defects, the same story. Oxygen pairs have the lowest energy and they are the most favorable. Cation exchange was a little bit more complex to study and simulate and actually realized what does it do. Here is just a visualization of the process. But energetic considerations show that in BSCF, we call it clustering effect, which can occur in both A lattice and B lattice. What does it mean, actually, that if you change barium and strontium in the lattice, it requires very low energy. Okay? Barium and cobalt exchange is more costly, and it does not happen that much. So antesite defects are costly, right, due to the need for the charge compensation, the difference in ionic radii of both atoms, and the different coordination number in ideal crystalline lattice. So we think that this kind of defects are probably not happening, or if they're happening, they're not that often and not that popular. Interestingly enough, in LSCF, similar trends were found in respect to this kind of disorder. Then we looked at Schottky disorder in BSCF and found that complex Schottky disorder indicates that segregation is favored in BSCF crystals with high concentration of vacancies. And then we wrote a whole bunch of different decomposition reactions. So what we found with Schottky-like disorder and clustering effect means that cations are not highly ordered in the material. And if that's the case, you immediately come with an idea that it's probably possible to decompose these complex perovskites in other phases. And these two equations actually show that. It also shows that the same reactions can occur in cubic phase and hexagonal phase, with vacancies and without. But the energies are different, and the obtained low energies for this kind of disorder confirm that significant solubility of metals within the corresponding sum lattices may take place, which was kind of explanation for experiments and what they saw in loss of performance of the materials and fuel cells. So these equations and energetic analysis suggest that BACF decomposes into other solid perovskite phases under ambient conditions. It also suggests that the cubic phase gains stability with an increase of delta as compared to hexagonal phase. At the right side of the slide, you can see hexagonal phases which has different energies for these reactions with vacancies and without. And comparison with cubic phase kind of say that stability of these phases is different. Then we went further and wrote even more equations for LSCF. And we saw kind of different energies and different dynamics of these reactions. So the decomposition reactions are endothermic, unlike BSCF, which implies that stoichiometric LSCF is more stable versus decomposition than BSCF. And just to remind you the previous slide, here are the energies. And you can see that for LSCF, even with delta equals 0, energy is endothermic, while for BSCF, it's exothermic for cubic phase, and it will decompose. And then we sit down a little bit and wrote another 30 reactions, and then another 30 reactions, and then we looked at probably all possible reactions for decomposition. We selected several of them, which are much more illustrative than others, and this table represents decomposition into simpler perovskites and oxides. And based on energetic considerations, both oxygen stoichiometric and vacancy-containing BSCF are thermodynamically unstable, which was kind of a big disappointment. Because of that, they expected to decompose at low temperatures into a mixture of several oxides, either with cubic or hexagonal phases or with combinations of both. And it can be done through several alternative routes, either through simpler perovskites or combination of perovskites and oxides. The same kind of reactions we tried to do for LSCF. It turned out that there are only fewer reactions than in comparison to BSCF which are possible here, and energetics of these reactions were also different. So chemically, there are fewer possibilities for decomposition of LSCF beyond perovskites than of BSCF, and it depends on possible oxides and combination of perovskites which can be a result of this decomposition. And based on energetic considerations, again, both oxygen stoichiometric and vacancy-containing LSCF are thermodynamically more stable than BSCF. Unlike BSCF, LSCF is expected to preserve the material's integrity in devices under a range of conditions. So to say that this is a solution, probably not, but at least LSCF seems to be a little bit better than BSCF in its behaving because it's more stable. So this is also illustrated here with vacancy formation energy depending on concentration of vacancies in both phases of BSCF, hexagonal and cubic phase. And you can see that vacancy formation energy in the cubic phase increases with the material's non-stoichiometry much stronger than in the hexagonal phase. High concentration of oxygen vacancies serves to stabilize the BSCF cubic phase, in which their formation energies are considerably smaller than those in the hexagonal phase, which is, again, was a little bit unexpected result, and it would be probably impossible to obtain without these calculations based on experimental observations alone. We also prepared phase diagram based on ab initio thermodynamics, which more or less surprisingly shows that we are very close to experimental range in which the stable phase is observed. We actually, based on the result and approximations, which are pretty rough, we did not expect it to be that close to experiment and reproduce the experiment as closely as we did, but that was the observation. So difference in the vacancy formation energy in two phases offers also an explanation to the large dispersion of delta measured experimentally. And when we reported this first at the conferences, it was actually a big disappointment because many people decided that all this work and all the money and all the politics which was invested in studies of BSCF was good for nothing, and BSCF is probably not as good for these applications as people thought for several years. However, despite the fast kinetics of the oxygen reaction and high conductivity, BSCF is kind of unsuitable for cathodes in solid oxide fuel cell applications. Well, just because it's unstable. It does show good properties for oxygen oxidation reaction, but since materials is unstable, the performance of the material will be lost very quickly under operating conditions. Just a little bit of more reasons to show how BSCF and LSCF is different. We looked at the diffusion of vacancies in both materials and discovered there is charge transfer. And this charge transfer in the transition state is different. In BSCF, there is a large charge transfer, which actually affects kinetics and diffusion barrier. In LSCF, it's not. So if we compare, so kind of our conclusion was that yes, BSCF is probably not that good for these applications, but we hope that it's not all that bad because LSCF is probably suitable, and based on this analysis and based on the comparison, it's possible to provide recommendations for how to choose the materials or how to prepare materials for this application. To show you just a summary of BSCF and LSCF studies and calculations of defects, stoichiometric crystals in BSCF are hexagonal, LSCF is cubic distorted. Recently we actually found that it's more orthorhombic, and distorted cubic and orthorhombic faces behave almost similarly, so it's difficult to distinguish between them. They probably coexist. Non-stoichiometric crystal, which has a lot of oxygen vacancies, is cubic in BSCF, and it's still distorted in LSCF. Oxygen vacancy formation energy is lower in BSCF. It's almost twice higher in LSCF, but it's not too bad. So 2.6, anything close to 2.9 is actually still suitable for these applications. It's the same as diffusion activation barrier. It's very low in BSCF, it's 0.5, and it's 0.8 to 1 EV in LSCF, and so forth. So there are a whole bunch of different properties which can be compared. Most important is that BSCF is unstable when it's stoichiometric or has high concentration of vacancies, and LSCF is much more stable than that. So we think that this will be actually good alternative. Okay, and to summarize this, BSCF lattice can accommodate a variety of defects and defect combinations which affect both the oxygen reduction and crystalline stability. Based on energetic considerations, BSCF is likely to be unstable under ambient conditions and tend to decompose into other perovskites. And this is not the case with LSCF, which kind of gives you a nice alternative for applications. With an oxygen vacancy formation energy in BSCF growing with delta in the cubic phase steeper than in the hexagonal phase, high concentration of vacancies actually serves to stabilize the cubic phase. So without vacancies, BSCF is much less stable under ambient conditions than hexagonal phase. And experiments, it kind of contradicts the experiments, right? So explanation is that when material has high concentration of vacancies, the cubic phase is stabilized. Both BSCF and LSCF show high tolerance to cation exchange, implying that cations are not highly ordered in the lattice. They're actually dissolved. Can you hear me still? LSCF has higher vacancy formation energy and higher diffusion activation barrier, but exhibit better stability of both stoichiometric and non-stoichiometric phases. So we think that this is probably better material for applications. And just to show the acknowledgement, there are a whole bunch of agencies which fund this work. Thank you.
Thank you. Do you have questions? Yep.
Hi. Just a quick question. When you calculate the defect formation energy, usually you take into account some chemical potentials.
I cannot hear you.
Sorry?
Cannot hear you.
Is it better like this? Okay. So when you calculate the defect formation energy, you have to take into account different chemical potentials, like each of the elements you consider, and also the Fermi level. Because with the charge state and depending where your Fermi level is, some vacancies will be more stable in different charge states. So what are the chemical potentials you have considered? Like, is it oxygen poor or oxygen-rich conditions?
We did both, actually, and it can be done effectively in VASP, right? Since you take differences in total energies, you don't have a problem. We did this using chemical potentials explicitly too, right? And the results were very comparable, so there was not a problem to do this.
Another question? Fine, everybody hungry. So we can thank Maya again. Closing the session, so there is no advertisement. Okay, so we can enjoy the lunch then.